Here is a science briefing on mixed phase clouds and snow. In this presentation, we will discuss mixed phased or cold cloud precipitation processes. We will describe how ice crystals are formed through ice nucleation. We will talk about the different types of crystals. And finally, we will discuss ice crystal growth processes, which include depositional growth, accretion and riming, and aggregation. So what is a mixed phased or cold cloud? A mixed phased or cold cloud is a cloud with temperatures below freezing, 32 degrees Fahrenheit or 0 degrees Celsius, and where both supercooled drops and ice occur in the cloud at the same time, as indicated by this figure. Supercooled drops are liquid drops when the air temperature is below freezing. Here's a diagram showing the percent of liquid and ice based on temperature. Clouds will not necessarily glaciate or turn to ice as the temperature falls below 0 degrees Celsius or 32 degrees Fahrenheit. In fact, supercooled water droplets dominate in clouds warmer than -10 degrees Celsius. The likelihood of ice in a cloud increases substantially at -10 degrees Celsius, as indicated by the diagram on the right. At -10 degrees Celsius, there will be a 50% chance of ice in the cloud. And as you cool down to -15 degrees Celsius, there is a 90% chance of ice in the cloud. So how are ice crystals or snowflakes formed? Of course, the temperature needs to be below 0 degrees Celsius or 32 degrees Fahrenheit. However, water in a cloud does not automatically freeze at these temperatures. In fact, pure water does not freeze until the temperature approaches -40 degrees Celsius, which is also -40 degrees Fahrenheit. Ice crystals need a ice nuclei to form in a mixed phase cloud. Ice nuclei are aerosol particles which enable water vapor or cloud droplets to freeze onto them to form ice crystals at temperatures colder than 0 degrees Celsius. The effectiveness of potential ice nuclei is dependent on structure. A similar structure to ice is best. Examples include clay and soot. And temperature. Ice nuclei concentrations increase as the temperature gets colder. After an ice nuclei forms an ice crystal, the temperature and relative humidity, which is an expression describing the percentage of moisture in the air, will determine its habit. The habit is defined as the type or shape of the ice crystal. Examples of habits are shown in the figure and include plates, dendrites, columns, and needles. Crystal type is dependent on the temperature and the moisture or relative humidity of where it is formed. So looking at the crystals formed above the water saturation line, or where the relative humidity equals 100%, this line is indicated by the red arrow. On the left side of the diagram, we see dendrites at the warmer temperatures, then needles at temperatures near 25 degrees Fahrenheit, then dendrites at temperatures around 5 degrees Fahrenheit, and columns at temperatures colder than -8 degrees Fahrenheit. Below the line, where the environment is not water saturated, we see prisms and columns at the warmer temperatures and plates and columns at the colder temperatures. Of course, please remember these are the temperatures and moisture conditions where the ice crystals are formed, not the conditions near the ground. This diagram shows the ice crystal growth rates as dependent on temperature in the horizontal axis. It is looking at the growth rates at 18,000 feet in the upper air, as indicated by the red line, and at the surface in the yellow line. The diagram shows that crystals have the best growth rates and grow fastest at temperatures between -11 and -18 degrees Celsius, or about 0 to 12 degrees Fahrenheit. As noted in the previous slide, this temperature regime is where you'll find dendritic crystals. Meteorologists often refer to this region as the dendritic growth regime, where very efficient dendritic growth occurs. You will usually find fluffy, light snow if the crystals grow in these temperatures and moisture conditions. The next few slides will discuss how ice crystals grow. The first way ice crystals or snowflakes can grow is by vapor deposition. During this process, cloud droplets in the vicinity of the ice crystal may lose mass to evaporation. Evaporation is a process where cloud droplets convert to water vapor. So in some ways, ice crystals grow by vapor deposition at the expense of the cloud droplets. Vapor deposition is a slow growth process. It maintains habit identity. For example, a dendrite will still look like a dendrite as it grows. The next way ice crystals can grow is through riming. Riming or accretion is when ice crystals grow by colliding with supercooled cloud droplets and they freeze on contact. In heavy riming situations, the ice crystal habit or identity may be lost and may be converted to a snow pellet or graupel. Graupel is shown in some of the images on this diagram. It typically has 3 types: cone, hexagonal, or lump. Finally, the last crystal growth mechanism is aggregation. Aggregation is simply ice crystals or snowflakes colliding with each other and collecting each other on contact. Aggregation can occur if fall speeds of snowflakes are different. It is a function of crystal type and temperature. For instance, dendrites tend to adhere or collect each other due to their branch structure, while plates and columns tend to rebound. Ice crystal surfaces also become stickier above -5 degrees Celsius, similar to the fact that wet snow tends to make the best snowballs. Here is an image of falling snowflakes showing aggregation of multiple crystals in each image from NASA. As aggregation takes place, the snowflake falls faster, collecting more crystals. Here is a summary of the solid precipitation types. The top 6 are crystal habits which have grown by depositional growth. These are plates, stellar crystals, columns, needles, dendrites, and columns. The next 2, 7 and 8, are crystals that have grown by riming, but you cannot figure out their habit. Number 9 is sleet, which is basically the refreezing of melted snow. And 10 is hail, which grows due to heavy riming and which occurs in thunderstorms. So how does rain form in a cold cloud? Ice crystals form in the upper cloud. This cold portion of the cloud is indicated by the blue shading. You can see the ice crystals on the left side of the diagram in the upper cloud. As snow falls into the warmer air, temperatures above 32 degrees Fahrenheit, as indicated by the green area, it eventually melts and falls as raindrops at the surface. So in summary, we have discussed mixed phase or cold cloud, which contain a mix of ice crystals and supercooled liquid water. We discussed ice nucleation, where ice crystals form when water vapor condenses onto an ice nuclei. We discussed the ice crystal growth mechanisms, where ice crystals grow at the expense of cloud drops by vapor deposition. Aggregation is the collection of other ice crystals and can further increase hydrometeor size. And riming and accretion is the collection of cloud droplets and change the identity of the ice crystal. Most of our precipitation in the Intermountain West, including rain, is produced by mixed phase clouds and involve ice phase processes. That concludes the Grand Junction National Weather Service science briefing on mixed phase clouds and snow.